Hi everyone, my name is Zihanlin. I'm gonna do the question 9 homework 8, so let's begin. So it tells to prove that if x1, x2 is a Markov chain, then it is statistically determined by second order probability masses, which is dp xi equals to xi, xg equals to xg for each pair of ig, any pair of ig. So we know that actually for a general sequence of random variables, it should be statistically determined by its nth order probability masses, which is dp xn equals to xn, xn minus 1 equals to xn minus 1, and then you'll have x1 equals to x1. So if we want to prove the Markov chain can be determined by second order probability masses, then what we want to prove is actually, because every general random variables have this format, can be determined by its nth order probability. So actually, if we can prove that this nth order probability can be transformed into the second order probability masses, if it is Markov chain, then we can draw the conclusion here, so then it can be proved. So here we want to rewrite this as from nth order probability masses into a conditional probability format. So we will have a p xn equals to xn under the condition and all the other random variables. So here we will have xn minus 1 equals xn minus 1 till the x1 equals to x1, and here we'll time the probability of other joint probability of other random variables. Start from xn minus 1 equals to xn minus 1 to the x1 equals to x1. Okay. So, and we know it is a Markov chain, then with the property of Markov chain, or we should call it the definition of Markov chain here, this conditional probability can be rewritten as pxn equals to xn under the condition xn minus 1 equals to xn minus 1, because we know that Markov chain should only the status at the n, which is xn, can only should only be determined by xn minus 1 instead of any other random variables. So yeah, so we can rewrite this conditional probability as this. And like this second term, the joint distribution of other random variables, it still can be rewrite similarly as the first format, like it should be equals to p probability of n x minus 1 equals to xn minus 1, and the condition xn minus 2 equals to xn minus 2 to the x1 equals to x1. And here the probability should be xn minus 2 equals to xn minus 2, and then to the x1 equals to x1. So here we can keep this first term, it should still be xn equals to xn, and the division xn1 minus xn1, and here it is this term with the property of Markov chain. We know similarly it can be written as xn minus 1 equals to x minus 1, and the condition xn minus 2 equals xn minus 2. That's it. And we now have this, and similarly as this, it can be written iteratively. So in the end, we will have a final format like xn minus 1 equals xn minus 1, times the probability of xn minus 1 equals xn minus 1, and integration xn minus 1 equals to xn minus 2. And we will have all other same format as this until the probability of x2 equals x2, and the integration x1 equals to x1 times the probability of x1 equals to x1. So here we can write this nth order probability masses into this multiplication by the conditional probability like this, and we know each conditional probability can be write as xi equals to xi, and integration xi minus 1 equals to xi minus 1. By the definition of it, it should be equal to the probability of xi equals to xi. Xi minus 1 equals to xi minus 1 divided by the probability of x minus 1 equals to xi minus 1. So here we already have this second order probability masses format, and we know for each kind of this term, for each term of it, it can be written as this format. So we know this whole equation can be determined by this second order probability masses, which means this nth order probability can be transformed into a format of this second order probability masses. Then we know that if x1, x2 is a Markov chain, then it is statically determined by second order probability masses. So the proof is done. So that's all. Thank you.